Hello everyone, my name is Mohammed Sabiul Hassan and I will be introducing you all the data structure assigned to our team, the Lightning Panthers. The data structure assigned to us was a buffer tree. So let me answer you the question, why buffer tree? So that's usually because operations on data become more expensive when data item is located higher in the memory hierarchy. An operation on data in CPU registers is roughly a million times faster than an operation on data item that is located in external memory. Obviously, that needs to be fetched first. These data fetchers are also called I/O operations and need to be taken into account during the design of any algorithm. Well, the main idea is that if you're only allowed to spend less than one I/O per operation, then we cannot for every operation go to the data structure on external memory, but we have to save some operations, buffer them, and then process them in a whole batch. As you can see in the poster slide, you can see out the initial design. There in the buffer tree, you can see there's an internal memory as well as external memory, and the buffers are present in the internal as well as the external memory. What they actually do is they usually select operations which are first added onto the internal memory, or even data which is first added onto the buffers of internal memory. When they pass on to the external memory, they are loaded onto the buffers of the external memory before being passed on to nodes. I'll let my friend Hamad continue on from here. Thank you.
About complexities, we'll first talk about B trees, such as in binary trees. Each operation takes O of log n to the base 2 IOs, and operations hence take O of log n, O of n log n base 2 IOs. Increasing the number of elements in a node and the number of branches in a B tree reduces the time to O log n to the base k IOs, where k is the branching degree. In a buffer tree, each node stores m by k elements, with m being the size of internal memory and k being the number of children of each node. That makes the one operations complexity as O of log n to the base m by k. All the buffering, flushes, buffering again, etc. makes the I/O operations to be performed in batches, as Sabi explained, which is until all the buffers get full, hence limiting our number of accesses to the main memory. The final complexity for n operations hence becomes O of 1 by k log n by k to the base m by k, or I can simplify it for you. That becomes O of 1 by k log n to the base k, because for every operation to take place, it has to be flushed down. Hence, this limits our accesses to the main memory and saves our time by a great factor. Thank you. So I'll now hand over the presentation to Salman. Thank you.
So we implemented our buffer tree in Python using this. And here we are going to describe some of the helper functions we made in the class of buffer tree. Firstly, the constructor of the buffer tree takes in a parameter t, which is basically the minimum degree per node, which signifies that what is the minimum and maximum amount of children each node can have. According to the properties of the buffer tree, the maximum amount of children for each node will automatically be the minimum degree multiplied by 4. After that, the buffer insert function basically inserts an element and an operation into the buffer of the root node. How it works is that there is a tuple which stores what element we have to perform the operation on and what operation we have to perform, which can basically be insert, delete, or search. When the buffer at the root node gets full, the buffer is automatically pushed down onto lower level nodes recursively until all the buffers in the tree are full. When all of them are full, the buffers at the second last level are emptied, and therefore the buffer at the root node gets empty again, and we have some more space to insert more operations. The print tree function basically prints the tree level by level and each of its keys. The in-order function traverses the buffer tree in order and prints the keys in an ascending order. Now over to Aga.
I'm going to talk about our application. The problem we are trying to solve is orthogonal line segment intersection, which is performed using a technique known as line sweeping. Buffer trees, due to their design, are used to solve dynamic batch problems efficiently. Line sweeping is one such problem. The idea is to find all intersection points between the lines that are being rendered onto the screen. We start with a vertical line on the left side of the screen and gradually move it across the screen. We maintain a list of line segments and check which line segment is being currently cut by the vertical line. The line segments are added to the buffer tree, and we check intersections between all the elements that are right now present in the buffer being cut. Then we remove the segment from the buffer tree.